Yeah, good morning, everybody. Yeah, and thank you for coming. I hope you had a very nice evening yesterday here at the tent and maybe also in the city of Münster. Yeah, because this is recorded, I will not comment what I just heard. Okay. I just want to start my presentation with, that this talk will be about safety. And as you know, safety is a prerequisite. It should be 100%. And very often, we have claims that people are saying, okay, here I have a cell chemistry which is safer than state of the art. And but there are very little safety measurements, and especially there are very little systematic safety measurements. And I hope that that can convince you that making systematic safety measurements is very necessary for fundamental research of new cell chemistries, including this one is not working. Maybe this one, no. This one, okay, now it works. So for lithium metal batteries. So if we talk about battery 2030 plus, and that means we talk about future cell chemistries, lithium metal is certainly one of that has the very high interest. Especially it brings us new cell chemistries, for example, in combination with sulfur and oxygen, lithium air batteries. But also it can replace graphite in a regular lithium-ion battery configuration. Before I start, I should say that I was very reluctant in taking over this invitation to talk, because I feel that when you host a meeting, and this meeting is hosted by Münster, by the colleagues who have made the organization, I felt like it's not appropriate that somebody from Münster should give the keynote. But my colleagues were very insistent and said I should do it. But I should also mention that this talk would be not possible without the work that is done, both by the group leaders who do the daily supervision of students and postdocs, but also by the students themselves. And I want to mention here Lukas Hellwig, who works at MEET together with Jonas Neumann, also from MEET. He has done the safety part of this presentation. And these two people were supervised by Markus Börner, who is I don't know whether he feels well because he was sick over the weekend. Maybe he's coming today. And then I also have short, but I think very important point, which is related to the performance of lithium metal, because performance is somehow related to safety. And this has been created by Sebastian Kühn from the Helmholtz Institute Münster, and also supervised by Isidora Czekislaskowicz, which you already know because she is one of the two main organizers from the local organizing committee. And I believe that these two, especially Markus and Isidora, could give a much better talk than I do. But again, I have been invited, so I will do my job. Just here, I should also mention that Helmholtz Institute Münster is 10 years old this year, and MEET is 15 years old this year. So we celebrate 10 plus 15, so 25 years of anniversary of these two institutions. Yeah. Okay, talk about lithium metal battery technologies. That's a big thing. And we see the market is big. At the moment, the demand on lithium-ion batteries is strong, and we know it's varying all the time. It goes up and down. We learned also yesterday that forecasts are forecasts and never the reality. But they have limitations, and one of the limitations is always set its energy density. And you see this here when you have a lithium-ion battery configuration, stack level, not cell level, so without housing, and a lithium metal battery configuration with liquid electrolyte in the middle, and a solid state battery with lithium metal. These are actually called solid state batteries. I find this very interesting. Do you know why? Because solid state sounds like safe, and lithium metal does not sound safe, okay? But it's really a lithium metal battery with a solid electrolyte. And because the solid electrolyte is a little bit more, has a higher density than the liquid electrolyte, if you use the same amount, you end up with a little bit less specific energy. But nevertheless, lithium metal batteries and solid electrolyte, this is usually a couple. And if you look at the literature, you see that there are lithium-ion batteries, and there is still a lot of papers. So if somebody says research on lithium-ion batteries is over, please tell all these people who publish these papers, okay? If the research on lithium-ion batteries is finished. And there's also a lot of work on lithium metal batteries. And remember, the key word here is lithium metal batteries. So a lot of solid state battery papers, which use lithium metal, actually use solid electrolytes to make lithium metal possible. they are not using the keyword lithium metal, they are only using the keyword solid state. So probably there are much more. So it's a big topic and it's increasing over the years, and we also have a lot of activity in industry with lithium metal batteries, some of them with so-called anode-free configuration. That means there is no lithium metal on the anode after assembly, but during the first charge it's deposited coming from the cathode. And some liquid electrolytes, some polymer, and some sulfidic. So we have everything both in academia and in industry. So it's really a big topic. What is the problem of lithium metal batteries? And this is very well known. Since 1989, it became very public because batteries which were on the market caught fire, is the so-called dendrite formation. I like to call it high surface area lithium because dendrite is just one of the many morphologies that can happen when you deposit a metal on a substrate, including lithium. And the safety goes down and performance also goes down. And here you see a picture from my diploma thesis in 1992. So you see already at that time, we were able to make crappy lithium metal batteries with a lot of dendrites after charge. And this actually also came in the news, and you see the battery here looks like a dynamite rod. And also it really happened while telephoning, you know, this very big telephones at that time, bricks, where you're called for obvious reasons with an antenna on top. They caught fire while calling, so conversation too hot to handle. And a lot of people who were working at that time gave up lithium metal work. This was actually the birth of the lithium-ion battery. And this is a very famous slide already. I presented it several times, but it's simply so nice to explain what happened with the lithium metal battery after the 1980s. And it's an idea that has been created by a colleague from Helmholtz Institute and has been realized by a graphical designer of our group. Basically, in the late 1980s, the lithium metal battery was dead. Companies have proven this. Exxon and Moly went bankrupt. Exxon, the guy, became a Nobel Prize. R&D beyond 2005 then led to the fact that we believed that lithium metal is handleable. The lithium sulfur and the lithium air era began. It was not time for solid state. Solid state was a little bit later. Toyota 2007 or so made first announcements. And also there was a very big interest from the automotive industry that they said, with present lithium-ion batteries, okay, this range of 200 kilometers or whatever, 200 miles, this is not enough. We want to have something with high energy density. So please give us this thing. And we scientists, we replied immediately, said, no problem, we have lithium metal. And we also have new tools and new, let's say, ideas, and we have better materials, for example, new separators, and later on the solid electrolytes that we can make the lithium metal battery come again. And so the lithium metal battery came out again, and whether it will be successful, so whether it will be the savior of our high energy density dreams, or whether it will be a zombie, that means it never is really alive, but we talk about it all the time, it's very open. I think it's a 50-50 chance. Okay, high surface area lithium metal deposits, there are quite a few. And actually, all of the lithium metal batteries, including solid state, fail after some time because lithium metal gets deposited more roughly. Okay, can be even hundreds of cycles, sometimes over thousands of cycles, but they fail because this high surface area lithium deposits. And high surface area lithium formation is really detrimental for performance and safety. That is already proven. I think most of the people who are a little bit longer in the field know this already. There are various morphologies. Here we have 4 that we prepared by ourselves. We have the so-called needle-like morphology, which is called dendrites. Then we have the mossy morphology, and we have a granular morphology and also nodular morphology. And especially the dendrite lithium, that's the worst with regarding to surface area, because surface area means more reactivity with electrolyte, safety, and coulombic efficiency. Okay. A lot of people are trying to make lithium metal better. And for this, we are trying many things. We use electrolyte additives, for example, in liquid electrolyte. And what we did actually some time ago, and it was for me like a really eye-opener about how to understand literature better that has been published, is we did basically 2 different base experiments. We actually used a base electrolyte, which is a carbonate-based electrolyte, and then we used VC and FEC, vinylene carbonate and fluoroethylene carbonate. So let's say the typical two additives in lithium-ion batteries as additives. And then we did cycling. And already when we open the coin cell, we see that there is a difference in the deposits. The coin cells, as you see, that are made in VC and FEC are different. And also they are different whether we assemble the cell in the glove box, that means under argon, and in the dry room, that means under dry air. And if we look at the cycling data for this lithium symmetric cells, for me, this is a cathode-free cell. Here we basically see that with FEC in the dry box, we get better cycle numbers. And with VC in the, with FE in the dry room, we get better numbers. And with VC in the glove box, we get better cycle numbers. So depending on which additive we are using and also which atmosphere we are applying or having for a cell assembly, we get very different cycle numbers. Okay. Now we come to the full cell behavior. In the full cell, it looks like this. Okay, red and black is VC. Red is in the glove box. Black is in the dry room. And we see, even though it's a symmetric cell, the glove box was better. In the dry room, it looks like that it really helps to do something in the dry room instead of in a glove box. And for FEC, we see an even stronger effect. So what was already in symmetric cells, we had a better performance in the dry room. But this performance is even then increased by plus 40% for the system in the dry room. So it's an enormous difference for a full cell, in this case, an NMC811 lithium metal full cell setup. This actually indicated to us, okay, especially because of the VC thing, something might happen at the cathode too, not only at the anode, because it's very clear that at the anode, because of the activity of lithium metal, something happens, and this is not something very spectacular. It has been observed in literature. So if you look at the CEI, the cathode electrolyte interface, you see that in the case of VC, we see linear carbonates, which are different in amount when we do things in glove box or dry room. But especially for the FEC, we see carboxylates, which we do not see in the glove box, which we only see in the dry room. So we have here a new species that is formed in the presence of dry air, which is not formed in the presence of argon in a glove box. And if we do then simulations, then we can see that carboxylates, for example, formates, can form by FEC reaction on the cathode. So at the end, we have an influence of what we are doing in a glove box in a dry room, which is probably stronger than the influence of the additive itself. Just look at the difference for FEC in glove box and dry room and the difference for ZVC in glove box and dry room. It is really enormous influence, and for this actually we have to regard now also the literature that is happening. So the conclusion is that the initial cell atmosphere has a considerable impact on the lithium metal battery performance, and we have up to 50% increase in lifetime. The initial cell atmosphere impacts SEI and CEI composition, and it's an important piece of information. So maybe just the solution for the good lithium metal battery with liquid electrolyte is to do everything that we did in the glove box, do it in the dry room. I'm not suggesting it, but the results are suggesting that there is some impact here. Okay, so it's very difficult to say what is a good and what is a bad lithium metal battery. But it's clear that a good lithium metal battery has to be safe enough. This safe enough thing we know very well from lithium-ion batteries. Okay, lithium-ion batteries pass safety tests. These safety tests have been specifically designed that lithium-ion batteries can pass. Okay, it's not like that somebody creates a safety test that all lithium-ion batteries fail. No, the safety test is created in a way that at least some of them pass it because we want to have them in our cell phones and in our cars. Still, we know that phones and also cars that have passed the safety test can catch fire. We have information about that. So that means the safety test does not tell us something is safe. The safety test tells us that something passes the safety test. Okay, and it's a moving target. As you may have heard, 2 years ago, China, who is now basically leading everything, including the standards. I was really surprised. As Germans, I thought we were the leaders in standards because we are very good in bureaucracy. But even here, the Chinese are in front. that the Chinese have created a new standard, which Chinese battery makers can fulfill, Germans not at the moment. And also maybe probably European. So it's really a very interesting thing. So that means in China, I think after 2026, all new cars have to follow these new safety standards, and they are more rigid than the old ones. And interestingly, CATL, only 1 hour after this has been published, already said, we already have the safety standard. It looks like that they talk to each other, the government in China and CATL, maybe. Lithium-ion battery-powered cars are set to catch less fire less often than combustion engines, but we also know that a burning lithium-ion battery is very difficult to handle for the fire brigade. It's usually extinguished with lots of water. And the aim is to cool the vehicle down, that we do not have the thermal runaway from one cell to the other, the so-called propagation. So how about lithium metal batteries? Okay, maybe for some of you it's a rhetoric question, but yeah, we went into it. So first of all we looked at some, let's say, basic calculation. So we actually looked at how much lithium metal do you need when you want to power an electric car with the same kilowatt-hour energy than a Tesla. So we took a 73.5 kilowatt-hour battery in a car, and for this you need 15.3 kilogram lithium. 15.3 kilogram lithium, or 30 liters of lithium, because lithium is a light metal and the density is not good. Actually, a lot of papers say it's a great advantage that the density is low. Actually, it's not, because then the volumetric energy density is not great. This actually includes a 200% excess of lithium compensating for losses that we have during cycle. If you would take a zero excess lithium metal battery, that's so-called anode-free system, then 5.3 kilogram, oh no, 5.1 kilogram would remain. 5.1 kilogram would remain. So still an enormous amount of lithium. So somebody of you who is a chemist might be thinking about, oh, so much lithium, and this is under my seat, okay? So much alkali metal, so reactive. But this is the truth if we would work with lithium metal batteries. And these 15.3 kilogram, when we would this stoichiometrically converted into hydrogen with the help of water during a fire, then this would create 25 cubic meter of hydrogen gas. And the combustion energy is enormous with 86.1 kilowatt hour of heat. Usually this is a little bit higher than the capacity of the battery. And there are other further potential hazards because lithium metal batteries are not so well investigated in regard to safety. So energy density, the molten lithium is very difficult to handle, and of course moves to the cathode and also makes solid state batteries and very unsafe. Porous lithium, the high surface area lithium that we talked about, and some unknown facts which we don't know. So there is something which is really interesting to know, and we should do some systematic studies. And we did it on small cells. Okay, so we did synchronized safety investigation at different levels. As you know, there are three types of safety that have to be regarded. Mechanical safety, typically addressed by so-called nail penetration tests. In China, this test is no longer accepted because basically most cells, even most lithium metal cells, pass it. So there are different mechanical tests now, like crushing and so on. Electrical abuse is, that means overcharge mostly, and thermal abuse. And here we will talk about thermal stability as critical safety property. And we do it on the material level, and of course on the component level, and on the cell level. And also we did some validation. That means we did several measurements to find out whether this is representative what we are measuring. And we used DSC on coin cells with a relatively small capacity and heat wave surge or heat wave seek accelerating right calorimetry on pouch cells with about 70 milliampere hour. Okay. What we see is that when we are looking at dendrites, that it's very important about what we are putting together as chemistry in liquid electrolytes. And this is well known, additives, which solvents, and also which electrochemical regime we are applying. This is a picture from 1989, which already shows to us that this has been done already before on lithium metal. And we see here three different morphologies of lithium metal, mossy lithium, dendritic lithium, and in between the granular lithium. The granular lithium is the one which is the more compact. So this is the one which is actually desired in liquid electrolytes. And then on the left, on the y-axis, we see the current density during charge, and on the right hand, on the x-axis, we see the concentration of the salt. So basically, research that we are doing today, we look at y-axis, for example, at the surface area to current density relations for structured lithium metal anodes, and we also work on concentrated, highly concentrated, or super concentrated electrolytes with a lot of salt or even only salt ion liquids. So this is from 1989. And basically, there's a very small range for electrochemical and chemical conditions where this, let's say, compact morphology happens. So you have to be very careful with what you are doing during cell assembly, but also during cell operation. So for us, this is extremely important because we don't want to do thousands of cycles in excellent electrolytes. We want to create dendrites very fast, because then we can look at what is the impact on dendritic high surface area lithium on the safety. So we use organic carbonate-based electrolytes because then we can harvest dendrites fast. And look at carbonates versus ether-based liquid electrolytes. In the US, for example, the ether liquid electrolyte stuff is much more important than the solid electrolyte stuff. So they have big programs running on liquid electrolyte batteries. And they work on ethers, and ethers are better in stability and electrochemical performance, but they usually have a lot of unsafety because they're usually more volatile than the carbonates, and also they make gases which are not very nice when you do a safety test. So ethers are not really the great thing when you do safety tests. If they make very, let's say, not so nice gases, maybe it's not even a great thing for consumer applications. And we looked at three different properties. We looked at the influence of lithium metal electrode thickness. We looked at the lithium metal deposition morphology depending on the current density during deposition, and we looked at the influence of EC and FEC-based electrolytes. So FEC, as you know, is the magic ingredient, makes silicon better, makes lithium metal better, so FEC should make it. Okay, we start simply with looking at heat wage third accelerating rate calorimetry tests on pristine and aged materials, left pristine, right cyclic aged. And we see for the pristine materials, the lithium metal reacts first with the electrolyte, but everything else is in the similar range. Okay, lithium metal is determining the safety. It's what's the lowest one, highest reactivity with the electrolyte, but the others are very similar. And everything happens at 150 degrees C plus when the lithium becomes soft and the SEI becomes soft. For cyclic aged, we see that for the NMC electrolyte and separator electrolyte thing, everything remains more or less the same. So it's again, beyond 150 degrees C, but the lithium metal moves down, the onset moves to 80 degrees C because we have created high surface area lithium. So a typical safety test at 90 degrees C would be already beyond the scope of this lithium metal battery. Okay. And now we are looking at the influence of the lithium metal thickness. And here we have four different thicknesses, 0, 20, 50, and 100 micron lithium. We see the 0 micron lithium, that means anode free, zero excess, means that basically after 20 cycles, the SOH is at 20%. So it's really, the lithium is used up very fast. For the other three, at least for the given cycle numbers, which are very small, 25, we see that behavior is very similar. And if we look at the SEM, cross-section SEM, you have to do this under very cold conditions, cryo, FIB SEM, because lithium is melting when you are using SEM at normal temperature. Then you are seeing that you have, with lithium access, similar capacity retention and also the similar top view morphologies, but they are different in the thickness. That is clear because we are depositing different amounts. We have different amounts of lithium that we are cycling. So if we are looking at the influence of lithium metal electrode thickness, we get the result that you see here on the top right. And you might say, okay, this is a little bit too small to watch from the back. For this reason, I have enlarged it. And here we see the thermal analysis. And on the right-hand side, in, let's say, more dark colors, green and blue, we see the pristine cell. So no cycling. And with red, yellow, and orange, we see the cyclic aged cell. And we see for the pristine cells, still everywhere lithium metal is the safety determinant component. We have a smaller self-heating rate for the pristine LMBs because we have no high surface area lithium, not such a big surprise. Around melting point, we have an exothermic reaction of the excess lithium metal. And this is actually not an endothermic reaction of lithium metal. That means heat is consumed. Actually, heat is created because we are heating up, but heat is consumed also because this is used for lithium melting. And cyclic aged LMBs show very similar thermal behavior. And at 80 degrees C, everything becomes very, very uncomfortable. Okay, if we look at what we do with the heating processes, as I said, we did very systematic studies. We found out that when we do 3 cells, everything is somehow different. Okay, and if we look, for example, at the DSC on the left, this is a 1-hour experiment. Then the DSC is done from room temperature until this more than 300 degrees C. We see that when the lithium is thicker, the temperature moves to the right. So that means the temperature becomes more safe for the pristine LMB. So that's very interesting because a lot of people believe thin lithium that is safer than thick lithium because we have less reactive components in the cell. But in this case, because the lithium melts and the lithium takes up heat during melting because it is an endothermal process, thick lithium is safer than thin lithium in the DSC measurement. If you go in the arc sequence, in the typical heat wage search accelerating rate calorimetric sequence, that means you're heating up for a couple of kelvins, then you're waiting many minutes until there is a value that you can take up, and then you're heating up the next kelvins. This is a sequence which can take 16 hours until you're on top beyond the melting point of lithium metal. And in this case, we see that the 100 micron lithium is the one which is you see better here. The 100 micron lithium, as you see, starts earlier than the 20 micron lithium. So here the world is okay. More lithium in the cell. You see that also in this case, we have better safety. But if we do it the other way around, you see that the thick lithium becomes again safer again. If we then really ramp it up without waiting, we simply ramp it up until 80 degrees C, and then we do the safety test, we see that the 20 micron lithium is reacting less than 100 micron lithium. So we always get different responses for different results. What is a realistic safety test? A realistic safety test is something which is close to what happens in a car. In a car, when you have a safety incident, does your cell heat up within 16 hours? No. But this is how all ARC data is produced in literature. Okay, so the thing is, safety is something which really depends on how you measure it. Okay, now we are coming on the influence of the lithium metal deposition morphology. And of course, this is nothing surprising here because, of course, at higher current densities, you have more high surface area lithium. But let's go for it and see what we learn. One thing what we learned is it does not work. We did not get any reproducible results. What was the reason? Okay, when you buy a coin cell, then you buy the typical coin cell. It is either aluminum or stainless steel. And then you put it together with a sealing. And this sealing usually contains polypropylene. And polypropylene melts at 160 degrees C, and the safety event of a lithium metal battery, the main thing is happening after 160 degrees C. So that means you are measuring safety on an open cell, or a cell where the sealing is molten, or the sealing is half open. And this gives you very reproducible results. Guess what is used in all DSC measurements in literature for sealing? It's polypropylene. So we changed this to a different polymer. And this polymer melts at 340 degrees C. And this helps us to get reproducible safety data for the DSC. Then we also changed the position of the lithium metal anode. We brought it very closer to the sensor, which basically means that you have to put the lithium metal anode in the bottom of the cell and not in the cap. Because the sensors, these are sample holders, and they are made in a way that usually the cathode is close to the sensor. And finally, also for the coin cell housing, you have to be careful that if you use aluminum, don't use it on the anode side. If you want to use it on the cathode side, because otherwise you have lithium alloy formation. So with these three things, we just started the safety test. We took this polyether ketone polymer, which allows us to make reproducible safety tests. And we see that after 10 cycles and after 50 cycles, we see that, of course, we are having more high surface lithium. So we have thicker porous layer when we are having more cycles, which is what expected. And basically, we can also watch this both by cross-section and also with top view pictures. And we see that the SEMs give us, let's say,
very similar deposits, but you see also that if you look here at the enlargement, that here we still have a lot of bulk lithium because it's only a few cycles, and here all the lithium is already used up because we have 50 cycles and we have more high surface area lithium. So when we look at the thermal stability in DSC, we get two different responses. One at around 100 degrees C and less. This is the high surface area lithium. And the more cycles we have, the more high surface area lithium we have. And then there is remaining bulk lithium, and this bulk lithium reacts then when the SEI becomes soft and also it melts. This is around 170, 180 degrees C. And you see that the lithium melting also consumes some energy. And also you see that for 300 cycles, there is very little bulk lithium left at 180 degrees C with almost a flat curve because all the lithium is already high surface area lithium, and this reacts around 80 degrees earlier than the bulk lithium. Then what is the SOC thing? It's also very clear. At the beginning, pristine, the safety response is basically 180 degrees C because before there is no high surface area lithium, and then you discharge. In the discharge state, you dissolve some of the created high surface area lithium. That means you have less reactivity than in the charge state. And of course, with higher cycle number, you increase the amount of high surface area lithium and have more problems here. Now we compare this to a lithium-ion battery. And this is, I think, for me, it was really an eye-opening thing because remember how lithium-ion batteries burn. Okay, they burn quite a bit. And here we see the lithium-ion battery below compared, and you see the heat flow is, you see it's a very different order of magnitude here. On this axis here, we go into the thousands, and here we had achieved even hundreds. And you also see here the onset temperature. This is in gray to the left, and the released heat to the right. Especially the released heat of a lithium-ion battery, nothing compared to lithium metal. And still we know how lithium-ion battery burn. So lithium metal battery will be, I would say, a new experience in case we have a fire in the car. So then we look at the lithium deposition morphology at different current densities before we had cycle number, and we see that the higher the current density, the more problems. This is as expected, but had to be systematically investigated. And we see also that the onset temperature goes down when we go up with the deposition morphology. And basically, we see that also, let's say the threshold is typically that lay at less than 0.5 C. That's the threshold where in liquid electrolyte, you get, let's say, reasonable deposits for lithium metal. Beyond that, you already are getting a lot of high surface area lithium. So this is a summary here, what on the DSC measurements, in addition to the little tips for making reproducible DSC measurements, I basically have shown that with cycle number, its current density, and also the state of charge, which is the charge state, you have a more unsafe situation. So proven as it is, but I think the extent is something which at least some of us maybe find is interesting to know. Finally, electrolyte composition. Can we do something on the electrolyte? And of course, I did not touch so far, solid state batteries. So it might be a little bit different, but also remember that liquid electrolyte have something that reacts, but also solid electrolytes have something that can react. And so oxides, for example, are very reactive with the anode. Sulfides are reactive at both sides. Polymers, it's well known that if you do something wrong in assembly, they can also catch fire. Of course, a plastic can catch fire. That's not something which is surprising. So also with solid electrolytes, these safety tests would be very important. Now we look at FEC and EC-based electrolyte. And basically, we are using here an electrolyte with only EC-DEC or only FEC-DEC. So the FEC is not used as an additive, it's used as a 30% component in the cell. And we see with FEC, at least for a given number of cycles, we see almost no degradation. So FEC is good, and the more FEC, 30% is a lot, the better for lithium metal batteries. If we look at the DSC, we see that with EC, we have an event at around 100 degrees C and less.
With FEC, it's flat. That means FEC is not creating high surface area lithium after 50 cycles. So this is actually good news. And the bad news is that when you look at FEC and EC, they also have a decomposition temperature. The decomposition temperature is usually lower than the boiling point. All of these cyclic carbonates are decomposed into CO2 and something. Something in the case of FEC means, for example, also HF. And this is happening already at lower temperatures, typically around 100, 110 degrees C. This decomposition happens, and this leads to a pressure buildup. So we made a temperature-dependent pressure analysis of 2 milliliters of EC and FEC electrolytes as they are in the cell, but without any electrodes. We put it in a pressure vessel and measured the pressure, and we see FEC gives us more pressure, so more gas evolution. Then EC, and the pressure difference is already in the range of several 10 bars after the temperature increase. So, and as you know, bars in the cell means tendency to explosion, so you might have a problem there too. So FEC is good for cycling, FEC is good for thermal stability in the DSC, but FEC is not good for keeping the pressure low in the cell. And here we see also the arc data, and also in comparison to a lithium-ion battery with the EC-DC-based electrolyte, NMC811 graphite cell, and we see the FEC and the lithium-ion battery, FEC LMB, and the lithium-ion battery behave very similar in regard to safety. Only the LMB with EC-based electrolytes already has a problem in the arc at 80 degrees C. So FEC can drastically improve electrochemical performance compared to EC-based reference. But I have to mention that this is a small cell. We have a limited number of cycles, and FEC is consumed during cycling because of the reactivity with lithium metal, so it might change over cycling. But to end this talk, let's say with a positive message, you can do something with the electrolyte to make lithium metal better. Unfortunately, only below 150 degrees C, because when it starts to melt, then lithium metal cannot be handled. So my conclusion, the overall safety properties have to be considered of a lithium battery. You have to do reproducible safety tests to do that. And then you can understand lithium metal batteries better. This is the first step to get a lithium metal battery to the market. The influence of the lithium metal electrode thickness has been investigated. The influence of the lithium metal deposition morphology has been investigated. And also the influence of different electrolytes has been investigated. And I would like to thank you all for your attention.
Thank you so much, Professor Dr. Winter. Very enlightening presentation. Are there